All right, limits at infinity. At infinity just means we would have to say positive infinity or negative infinity, either one. And that just simply means that we're looking at the end behavior of a graph. So what's kind of going on out to the side. Now, you've done this a little bit before back in algebra. What we're going to look at is more of the reasoning kind of behind it as far as that's concerned. So let's think about some of these ideas. If I had the limit as x approaches infinity of 3 over x. All right, so we're just working our old limit functions. This is not uncommon. We know what this looks like. Hey, if I can put infinity in and figure it out, I will. If I need to do some other manipulation algebraically or try values close or graph, we can do those kind of things. But here, when I'm talking about 3 over x, if I put infinity in for x, 3 over infinity, that's approaching 0. Will it ever get to 0? No, but it's going to get really, really close, that 0 piece. So that amount would be 0. Again, infinity, large number. Think about 3 divided by 100, 3 divided by 1,000, 3 divided by 10,000, 100,000. That's just going to get closer and closer to 0. Well, let's look at something like this. Maybe change it a little bit. Use your thoughts on this. Let's say instead of 3, let's go 5,000 over x. Still limit as x approaches infinity. Now all of a sudden, that's a 5,000. 5,000, much bigger number than 3, but it's still going to be 0. Okay? So this limit would still approach 0. Yeah, it's going to get there a little slower than it would in the 3 over infinity, but it's still going to get to 0. And it doesn't matter how many zeros I put behind this. Make it 50,000, it's still going to 0. 500,000 is still going to 0. Something like that. Let's take this a little bit further. Let's go limit as x approaches negative infinity. All right, so we'll use negative infinity instead of positive infinity. And let's just say 1 over x plus 1. Well, negative infinity, so negative largest number you can possibly think of, plus 1. In the grand scheme of things, the plus 1 just is not going to matter at all. It's not going to change anything. It's not going to help anything. It's not going to do anything like that. Right? So it's really talking about a constant value over some really large number. You're still going to 0. It doesn't matter if it's negative. 0 doesn't have a sign to it, positive or negative. So it's just going to approach that 0. This 1's not going to change anything. And let's make that 9,100, and it's still going to 0. It doesn't matter. All right, so the basic idea would be, if we have a constant divided by infinity, I don't care if it's positive infinity or negative infinity, that is still going to go to 0. We're looking at a constant divided by some extremely large number. That limit value will approach 0 for that piece. Now, let's look at some different ones here. So again, I'm going to write down what I said a minute ago. Limit as x approaches infinity of some constant over x. Hey, that's going to go to 0. Well, let's look at some situations when we wouldn't have just a constant up there on top. Let's take a look at the limit. X approaches infinity. Let's go 2x plus 1 over 3x minus 5. Okay. So definitely look at one where I don't have just a constant there and a variable on the bottom. Now I'm stuck with a variable, a numerator and denominator, and that's okay. This is a fraction. So what I'm going to do is rewrite this. And I'm going to divide the top by x and the bottom by x. Now, being that it's a fraction, I can do anything I want as long as I do it to both the numerator and denominator. So I'm dividing both by x. Why am I picking x? because I'm trying to create this situation of a constant. All right. So let's look at how this would reduce. Limit as x approaches infinity. That would be 2 plus 1 over x. So that x's would cancel there, 1 over x, over 3 minus 5 over x. Now when I substitute that infinity, 1 divided by infinity is 0. 5 divided by infinity is 0. So now we're going to have 2 plus 0 over 3 minus 0, 2/3. 2/3 would be that limit value at infinity. Now, if I went back and changed this to negative infinity, it wouldn't change anything because these would both still be zeros. And I'd still have that 2/3. Okay. Well, let's take it a little bit further, get some different powers up there. Let's say I had limit as x approaches, and we'll just still stick with the positive infinity. It's not going to change anything versus the negative. Okay. And let's go with, let's get a square in here. Let's go x squared plus 3x minus 2 over x squared plus, I don't know, we'll go 5. All right, so just trying to get a different look as far as the exponents. And we can even put, let's put a 2 in front of that guy. We'll go 2x squared plus 3x minus 2 over x squared plus 5. Now I want to grab that constant. So what I'm going to do so that I can get the constant value back above the variable is I'm going to this time divide both top and bottom, numerator and denominator, by x squared. Divide those pieces by x squared. Again, I can divide by anything I want as long as I do it both numerator and denominator. So let's see, this would simplify too. The limit as x approaches infinity. Right up top, you'd have 2 plus 3 over x minus 2 over x squared. And on the bottom, 1 plus 5 over x squared. Now, these last three pieces there, 3 over x, 2 over x squared, 5 over x squared, they're all going to go to 0. All right, it doesn't matter that it's x squared versus x, it's still going to go to 0. You're taking a constant divided by some infinite amount, whatever this is. All right, so infinity squared is still infinity. So this would become 2 plus 0 minus 0 over 1 plus 0, which is 2. There would be that piece. All right. Let's take one other look here if we mixed up powers. Okay. I say mixed them up. Had a different power, top and bottom, I should say. Limit, x approaches infinity. And let's go 5x squared minus 1 over 10x cubed minus 3x plus 2. So I've got a square or quadratic on top, cubic sitting there on the bottom. That's fine. I'm wanting to get this thing reduced down because I sure like these numbers over some variable. Numbers over some variable. And we don't care if that was a single x or a cubic. It's still a number, a constant value over a variable. So that means in this guy right here, what I'm going to do is divide top and bottom, numerator and denominator, by x cubed. Now the reason it's x cubed is because I'm selecting the highest power. I need the highest power to make things cancel out. I can't make it cancel out using the lowest power. So if I work this out, limit, x approaches infinity. Let's see, up top here you'd have 5 over x minus 1 over x cubed. The bottom, you cancel there, so 10 minus 3 over x squared plus 2 over x cubed. And so I'm looking at 0, 0, 10, 0, 0 when I substitute infinities in. So we would have 0 up top over 10, and that's 0. So that limit would be 0. Okay, let's take a look at one last one here, and then we'll kind of talk about these a little bit. So again, we sure like this guy, constant over. Constant over is going to give us that 0. Let's look at one where the power on top is larger, something that's larger. Let's go limit as x approaches infinity. And let's go with 5x to the 4th plus 3 over 2x cubed plus x squared. Right? So this time we got a larger exponent in the numerator. So I want to divide by that largest. That largest one's what's going to help me some. So I want to divide numerator and denominator by x to the 4th. So I'm just writing it out. Top divided by x to the 4th. Bottom divided by x to the 4th. Now if I reduce that down up top, we're going to have 5 plus 3 over x to the 4th all over 2 over x plus 1 over x squared. Reduce that down. And now, if I kind of simplify this piece down, I end up with a 5 on the top. It had 5 plus 0 on the top. And on the bottom, 0 plus 0. Right? And this is where we kind of have to really pay attention to what's going on. So up here, this would be 5 plus 0 over 0 plus 0. Now what we need to make sure that we understand and realize is this is really not 0. This is real 1 over x. It's really not 0. It's approaching 0. It is approaching a 0 amount. So if I take 2 and add something really extremely close to 0, it's still going to be a 2. Okay? If I take 5 and divide this by something extremely close to 0, that's actually going to be infinity. So I have 5 divided by something. I'll put 5 over really close to 0, and that makes it infinity. So we're saying, if I did 5 divided by 0.1, 5 divided by 0.1, that would be 50. 5 divided by 0.01, that would be 500. 5 divided by 0.001 is 5,000. Divided by 0.0001 is 50,000. So as this gets smaller, closer to 0, this overall fraction is actually getting bigger, right? Going to that infinity. Now, let's look at some things here as far as some things that are going to kind of help us. When we're talking about the end behavior of a function, that means what's happening at the extreme left or extreme right. Okay, so let's think about this. A graph. Okay, if you're going to draw a graph out to the right or out to the left, it either goes up to infinity, goes down to negative infinity, it oscillates like a sine function. It's not going up or down, it just keeps bouncing back and forth. Or it goes out along a horizontal asymptote. That's the only ways that your graph can end up going out to infinity or out to negative infinity. Graph's either going up, down, horizontal asymptote, or it oscillates. And again, the easiest oscillating function to think of would be like a sine or a cosine. Now, what you had before, you had some rules for horizontal asymptotes. And this was back in algebra. Okay? So your rules for horizontal asymptotes were if the top power is less than the bottom, it's 0. If the powers were the same, leading coefficients. If the top power is greater, there's not a horizontal asymptote when you were dealing with rational functions. Cool. I had this word constant up here. I'm just going to go back and rewrite. Here's like one of our original ones that we saw. Limit as x goes to infinity, 3 over x. We said, all right, that's 0. Let's use those old rules. Hey, top power is less than the bottom. 0. If the top power is less than the bottom, it's going to be 0. If the top power squared over a cube, top power is less than the bottom, it's going to be 0. If the powers were equal, like these two middle ones, x over x, leading coefficient, 2/3. X squared over x squared, leading coefficient, 2 over 1, 2 was that horizontal asymptote. So back then in algebra, they gave you the rules and said, well, know these 3 rules. If the top power is less, it's 0, horizontal asymptote 0. If the powers are the same, it's the leading coefficients. If the top power is greater, here was a 4th over a cube, there is no horizontal asymptote. There is no horizontal asymptote. Now you're actually in calculus here and seeing why that works. And it's all based on this guy right here. I'm going to take a number and divide it by infinity. I can reduce these fractions into this format. All right, so I can see where that's coming from to get the 2/3. Same thing here. I can reduce the fractions into the format where I have these constants or a constant over a variable to simplify that piece. Yes, if you still have memorized those rules, or now that we've talked about them, you're thinking, oh yeah, I remember those. I've done those before. I remember that. Yes, you can still use them. This lesson is about showing you the proof as to why that works. Why you're ending up with same power producing that horizontal asymptote, a different power if top's less, why it produces a 0, a different power if the top's greater as to why it produces not a horizontal asymptote, so in other words, not 0. Now, some ways to think about that. I'm going to revisit this guy right here. All right, so again, those rules still work. So if I had something like this, limit as x approaches infinity, 5x to the 4th plus 3 over 2x cubed plus that. I'm just rewriting the same problem so we can kind of investigate how we got this infinity. What we were saying back in algebra was, hey, you know what? This doesn't have a horizontal asymptote. And it doesn't. And we work it down using that reduction method, and it shows that it's not going to have one. It's not coming to some finite value where the graph will just level off along there. If I see the powers greater, I know there's not one. Infinity. Well, that's a bigger infinity than the bottom one. A 4th degree infinity is bigger than a 3rd degree infinity. Adding or subtracting something isn't really going to change anything. That's why even in these others, it didn't matter. Adding or subtracting something to infinity is not going to bring us back from infinity. We're already there. So I would know this answer is infinity. The top power is bigger. It's got to be infinity or negative infinity. In this case, it's going to be infinity. Okay, now let's watch what happens here. I'm going to change this guy to negative infinity. We change that to negative infinity. All right, well, top's bigger. 4th over a cube. So I know there's no horizontal asymptote. All right, which means this graph is either an oscillating function or at the end behavior, which negative infinity would talk about back this way what's going on. That means it's either going up or down because there is no horizontal asymptote and it's not an oscillating function. Let's investigate the negative piece. This would actually be negative, and this is why. If you take a negative value, and this is negative infinity, and you raise it to a 4th power, that's a positive. I don't care if you multiply by 5 and add 3, it's still positive. If you take a negative number, negative infinity, and you cube it, if you cube a negative, you get a negative. Times it by 2, it's still a negative. Right? So I basically have a positive divided by a negative is going to produce that negative infinity. So let's review a little bit based on some things we learned. Limit x approaches negative infinity. 2x minus 1 over x squared plus 5. Hey, that's 0. Top power is less than. It's going to give me 0. If you want to prove it through the reduction, you divide everything by x squared to get back to 0. Limit x approaches infinity. 3x squared minus 2 over 6x squared plus 5x minus 1. Powers are the same, both x squared. And that's going to be a half because we're going to go off of these leading coefficients, 3 over 6, which just reduces to a half. Here's my horizontal asymptote. Limit x approaches infinity of, I don't know, let's go 3x to the 5th minus 2x plus 1 over 2x squared minus, or we'll go plus 3x. Let's go this time negative infinity. Well, when I look at that, the top power is bigger. Since that top power is larger, there is no horizontal asymptote, and that's okay. That means my graph is now going up or down or oscillating. This is not an oscillating function. Right? It's not a sine or cosine or anything like that. So that means my answer is either infinity or negative infinity. It's one or the other. Let's take a look at our signs. My focus is really just right here. Anything I'm adding or subtracting isn't going to affect the infinities. I'm already there. So in that numerator, 3x to the 5th, if I have a negative infinity raised to the 5th power, hey, that's still negative infinity. A negative to the 5th power is negative. But a negative squared is positive. So now I have a negative divided by a positive. Okay, that's a negative. Something like that. Let's give a different look here. Limit as x approaches infinity. 3x over the square root 4x squared plus 10. Now, we can do reduction formulas and things like that. So in this case, I divide everything by the x squared. But let's think about what's going on. When we're looking at this, we need to think about, hey, infinity means in behavior. Do I really care about anything else other than out there at infinity? And no, I don't. I don't care about anything before then. I'm worried about at infinity, which means to me, plus 10 doesn't mean squat. It's not changing anything way out there at infinity. In comes the exponents. Well, a lot of times what will make us kind of think twice or, oh, slope, I see that square root. Okay, I'm thinking about exponents. Okay? The square root of x squared is x. Okay? The square root of x squared is x. So when I'm looking at that, it's going, well, wait a minute, that means these two have the same powers. So this is, think about it as, I'm going to say think as 3x over 2x. Square root of 4 is 2. Square root of x squared is x. This is really singular power, singular power. These powers are the same. Leading coefficients, 3/2. There would be my limit. It's still that leading coefficient. It just has a different look there in the beginning because of the square root. Remember what a square root does. It's going to half whatever power this is. Now, I'm not saying that 10 doesn't have an effect on the graph, but what I'm saying at infinity, it doesn't have effect on the graph. We're way out there. It's not changing anything. I mean, if we're going to take infinity and square it, times it by 4, that big, large number, think about it, adding 10 is not going to change anything. All right, so it's not going to have effect out there. I'm looking at what my powers really are. I've got a singular power. I've got a power of 1 because the square root of x squared is 1, so now I have the same power. There's those leading coefficients we're looking at. So it brings back in those old algebraic rules while giving you some proof to it. If you want to see the reduction proof on something like this, I would divide everything by x squared. So it would look like this. Or actually, by the square root of x squared, which I know is x, but this x squared is the highest, but it's in the square root. So I divided it by the largest power. Well, this right here would reduce to 3. Because x squared, square root of x squared is x. X is canceled. And on the other part, I can picture this being inside. This would become the square root of 4 plus 10 over x squared. So x squared going into each part. Now when I put infinity in, this is 0. So you'd have 3 over the square root, 4 plus 0, which is 3/2. There's that reduction piece, work the same way. And how we're coming up with those exponent rules that help us with the horizontal asymptotes. Now, as far as the limits of infinity, we came back to limits this lesson. Why would we do such a thing? Well, think about it. We've been working on parts of the graph, and the M behavior is a part of the graph. We need to know what's going on the extreme right and then over on the extreme left of the graph when you're looking at it. What's happening for those pieces, right? So previously we've been talking about what's going on in between, mins, maxes, inflections, concavity, increase, decrease. Now I'm looking at what's happening on the very end of each graph, going back to my old limit idea.